Hello, welcome to the final design review for Team Erato. Our product is the Badminton Buddy. Um, to start, oh, we would like to introduce the team super quick. Everyone in order, first go off. Duncan.
Oh. Hi, my name is Duncan tomorrow, and I'm a mechanical engineer.
My name is Sahith Obbu. I'm also a mechanical engineer.
My name is Leonffu, and I'm computer engineering.
I'm Kyin, and I'm an electrical engineer.
Hello, I'm also a mechanical engineer.
Hi, I'm Annie. I'm a computer engineer.
Hello, I'm Lorenzo, I'm a mechanical engineer.
I'm Ethan, mechanical engineer.
I'm Paco, and I'm a mechanical engineer.
Awesome. So first we wanted to again reiterate our problem that the entire project was intended to address. So badminton is one of the huge sport played by 2 or more people. It has over 200 million players in the world. And one of the issues with such a fast growing sport is that there's not enough supply of trainers. Hiring coaches becomes expensive. And so at gyms, what ends up happening is that classes get clogged up with a bunch of people that want to learn how to play and not enough people that can teach them. What we then saw in the market was that a lot of bots are not dynamic or engaging enough as training mechanisms to help people improve in a way that would make them want to continue playing. So as such, we started formulating solutions using a host of methods as we can start to get into right here.
So this is our objective tree we made last quarter. And of all our system, we want it to be a very simple device and branching that out, reliable operation, accessible, effective design, and high performance. If you go to the next slide, we can see the weighted objective tree. And then this will show you where most of our time should have spent or was spent during the process of this quarter. As you can tell, some were more important than others. For example, Simple UI took up at least 10%. If you watch the rest of this presentation, you can see how nice of a website that has been made or how simple the chassis has been made. Our chassis is portable. And due to our scope, some of these things weren't able to make, such as motorized wheels or just like a drivetrain. Some computer vision were out of our scope, but some other things were definitely thought of when looking at our final design.
And stuff will be expanded upon in a little bit.
So we've performed some product market research, and the first product we looked into was the Robo Mintoner, and it's basically a reactive badminton that has an XY drivetrain and that uses a mounted racket to return hits. It offers 2 rackets that are attached to an omnidirectional motion platform, and that is also attached to a linear motion gantry. The second product is the Siobasi shuttlecock launcher, and it comes in at around $3,000. It has a Birdie capacity of 180 pieces and can achieve 3 degrees of freedom with 33 degrees in the XY direction. It also has a remote control that controls speed, direction, and frequency. And the final product is the G10, which cannot return shots. It's not capable of varying shots or being customizable, but it is cheap. And so we looked into cost, automated intelligence, programmability or customizability, varied shot selection, and the challenge to skill ratio. Next slide, please.
So through all this design and stuff, we started coming with a list of qualifications that we really wanted to match at the beginning. We wanted a motion package. We wanted the cart to move, and we had the idea that it would go around about 2.5 meters per second and accelerate at the fixed speed. We wanted the launcher angle to vary in degrees from a positive to a negative. As such, we would be able to deliver all variety of shots, such as lofted shots or smashes, with a very high launch velocity to really mimic what a professional would be able to do. We wanted to have enough storage such that in this system, we would be able to continuously do long drills that would actually engage the player and have accuracy in guaranteeing that, if a user input specified a specific location on the court, we could then match it from our bot or our product. We wanted a body that was generally lightweight and mostly made of high density polyethylene, such it wouldn't then be able to withstand all the forces, but also not be super heavy. Some more customization on like location and velocity, and understandably, we figured that the product cost would be quite high. Over the quarter and the 6 months, we have refined some goals. These will all be expanded upon in the future. We had to remove the idea of computer vision. We scaled back the chassis and the idea of full motion mobile base, and a lot of improved safety concerns that we wanted to address. We decided to then continue the previous deliverables of having a launcher that could change direction and alter trajectory, which we will continue talking about in a later step. Some of the problems that we encountered were again, the scope of the project as determined initially, specifically the drivetrain and computer vision. We just figured that a lot of these considerations were not within something that we could feasibly do in 3 months. One big thing we seem to have overlooked at the initial forgo was the safety of having these wheels spin at such high RPM. So building upon those and the consistency, we addressed them by having safety concerns and measures, and fixing and altering the parameters in which our system could be used.
For the design and engineering work, as far as systems go, we designed a hardware system diagram and a software system diagram on the left-hand side. The software system diagram is all the software that we would use on the Raspberry Pi. We developed a lot of it, including its GPIO interface, its API server and networking, and its interface with the rest of the hardware. But since we scratched off computer vision, we ended up not going with the Raspberry Pi, and later you'll see a diagram of the updated, not Raspberry Pi system diagram. On the right-hand side, you can see the hardware diagram. I think Kyin might want to talk about that.
You can talk about the horror abstraction here.
Okay, I guess I'm going to talk about the hardware. It says Raspberry Pi there, but it's not supposed to be a Raspberry Pi. We're using the ESP8266. It's a Arduino-like microcontroller, which interfaces
can you
all
go
the
to the next
hardware.
slide, please? Sahith Mike will talk about this.
Yeah. So via PWM, it can control servos. Via PWM, it can control the motor controller, which controls the flywheels. The flywheels have encoder values read back to the microcontroller. That way we can synchronize the flywheel speeds. And all this is powered via the battery we have. The microcontroller we're using has a Wi-Fi built in, and we've created an interface off of that Wi-Fi. So when we got all the hardware working on the device, we're able to abstract it, which allows us to connect or control all of the hardware just from the UI on a cell phone or any other Wi-Fi enabled device. Next slide, please.
Yeah, so with that, I put together 2 different PCB boards or prototype boards. One of them is a voltage regulator that regulate or convert voltage 12 volts to 5 volts. So the 5 volts is used for the ESP, to power ESP, the motor controllers, and the 12 volts is directly connected to the motors. We have 4 motors in total, 2 for the flywheels and 2 for the arms of the separator. And then 4 motor controllers for all those 4 motors. And then then the other board, the other prototype board have the MCU that we're using, which is the ESP, as you can see in there. And also there's a a level converter on there, which is for the encoders of the motors. Yeah. So all these wiring cables and all these soldering is completed and is ready just to be mounted on a mechanical system. Yeah, next slide, please.
Another engineering work that we did was computer vision. We got some of the computer vision up to the point where we can do blob detection. Next slide, please. So this kind of demos the blob detection. It's just using the simple color detector to detect white color on the birdie. And as you can see, it's still a little, it fails to detect the birdie accurately. Kyin did some more extra work on it.
Yeah, see, can you like exit the slide and then come back in real quick? Like, escape and then, yeah, okay, slideshow. Oh, you don't have to do that. No, yeah, share again. There you go. Yeah, can you play that second video? Yeah, so I did more work to detect the birdie specifically. So as you can see in the video, when I throw the birdie into the frame that's determined by the blue box, it actually locates the birdie in there. I'll play the video again, and I also record the coordinate of where the birdie falls in there, relative to the frame. So this was actually a test done to initially when computer vision was in our scope to figure out where the birdie is going to be on a court when the birdie get launched to help calibrate where the birdie is landing at, so that the user didn't have to physically record it down on the UI to help calibrate. So this was supposed to be an automatically calibratable badminton buddy, but then we have more stuff to focus on mechanically. So we kind of scrapped this proof of concept out, but it was working in our way. But if we have more time, we could have actually implemented this. And plus, this would have involved using Raspberry Pi, which would have been a little more complicated when it comes to interrupting, and then parallelly working with all the motors that we have. So yeah, next slide, please. Yeah, I can show that video too. But it doesn't matter.
Okay, so this is our drivetrain iterations that we eventually scrapped for the final problem. But at first, I wanted a very complex four-wheel drive or two-motor four-wheel drive drivetrain with a 4:1 gear ratio using conveyor belt. Obviously, this was way too complicated for the machine we needed to go for. So I simplified it down to a two-wheel and a stroller type mount. And this was going a bit too simple. So I used a VEX hardware system with U channels and omnidirectional wheels for easy assembly and better for the final mount. But like I said again, due to the scope of our project, we could not be able to make this in reality, but analysis was done for these works. Next slide.
So in regards to the separating system, this is one of the more, I suppose, intricate parts of the mechanical design, because it requires very specific dimensioning in order to separate a single birdie at a time. So one of the first designs that we came up with was what you see is called the spiral loader. And the way that this works is it rotates, and as it does so, the birdies fall down. They're sort of like threaded downwards through the tube. And once the bottom birdie has fallen, the top part of the spiral will catch on the birdie that's above it. This design relied heavily on the presence or absence of friction between the spiral ends and the birdie feathers, and was shown to be inconsistent across multiple trials. Different types of birdies in different conditions yielded different results. And in order to test this spiral loader mechanism, the distance of the servo and the rotational speed of the spiral were varied.
Yeah, and another design we looked into was the rotating plate design. So on the slide, you can see two iterations of the plate design. The first incorporated sort of a catch mechanism that prevented multiple birdies from falling through at once, while the second used a plate that was perpendicular to the first plate design. And so the plate would flip one way and supposedly allow one birdie to fall through and then flip back and still hold up all of the rest of the birdies. And so to test this rotating plate mechanism, the axial distance of the continuous servo from the center of the birdie holding column was varied, as well as the rotational speed of the plate. And while it relied less on the condition of the birdie and the type of birdie used, it was shown to be less consistent and have a lower success rate than the spiral loader design, which was the principal design at the time.
For the pin design would work by having one birdie fall onto a platform that has pins connected to the top of it. A servo is connected to the platform that when it rotates the platform, the birdie will fall into the loading mechanism, and the pins will move and connect through the holes of the next birdie to hold it still in place. The servo will rotate again to move the pins out of the birdie, and the birdie will fall onto the platform. And then for the semicircle design, a semicircular disc would hold the bottom birdie in place, which would hold the other birdies on top of it in place as well. The discs, which are connected to a servo or motor, would rotate. So the top disc would rotate to hold the second to bottom birdie in place. And the bottom disc would rotate out of the way, letting the bottom birdie go and fall into the loading mechanism.
And finally, with the mechanical hands design, this is the separating design that we ultimately decided to use. The initial version of this design involved two mechanical hands powered by two separate continuous servos, which the hands would then catch onto the birdies and push them downward into a loading system. Our original goal with the other designs was to create a mechanism that only required one servo. However, due to inconsistencies that were shown during testing, we decided to move forward with the mechanical hands design. And I'm going to share my screen really quickly just to show some things. Okay, so as we can see here, this is the mechanical hands design. I'm going to talk about one other thing as well. Basically, the birdies are stored in this tube, which then can be placed onto this device for easy loading and easy storage of the birdies. And then this radius here is too small to the point where the birdies cannot fall through by themselves. So they come down here, and then the servos will power these hands to pull this down. Now, one of the important things to note is that we rely slightly on the flexibility of the birdie material. As you can see here, there is slight interference with the birdie itself when the hands catch on. But we're actually intentionally doing this so that it's able to push it down more consistently. Also, one other quick thing that you may have missed during the slides is that we were shown an image of this device here, which is sort of our original baseline idea for how we would get the birdies to transition from being separated into a position where they could then be moved into flywheels that would launch them. So this was 3D printed and tested, and it was shown that it was indeed able to catch the birdies here. And when the tips would go into the flywheels, the birdies would launch outward. And sort of this was used as sort of the baseline and inspiration for later design. You can go ahead and resume. Okay, cool. So here are just some of the videos of the testing. If you're able to play it in full screen, please. So as you can see, the spiral design did work. We held it just for testing, but one of the main reasons that we decided to move on, even though that design did work somewhat consistently, is that, like we said before, it relied heavily on friction. So it would actually damage the birdies as it would press into them quite significantly.
Lorenzo, Paco.
Yep, and that's all for the videos, but we'll talk about the future design iterations in the next slides.
So this is the
Okay, I can take
yeah, okay, go for it.
So this is the final design of the storage separator system. CAD of the final design is shown with one picture showing the housing closed and the other picture showing only one of the halves open. The two rods sticking out of the picture in the right would connect to the other half through a mount to close the housing. Next slide, please. So this is the final CAD design for the separator system. It is designed in different pieces, in split pieces, where you have the outer shell of the housing on the left that would cover the motors and wires. There is the interface part that is shown in the middle that would mount the motors and slides into the inside shell. The rods shown on the faceplate of the housing are separate parts that enter through the plate and would enter through the inside of the housing shell, where they would be screwed in at the back end of the housing. The motors are connected to a plastic arm that would press fit onto the motor shaft. The arms would rotate synchronously in the opposite direction to pull the birdie out of the barrel and into the loading system. The barrel is a plastic tube with plastic threads at the end that would screw into the housing when it is shut closed. Next slide, please.
Here is the prototype assembly. We purchased a metal and hardware kit from Vex Robotics, and then we designed mounts which are adjustable and allow for all components to be placed with ease. This assembly was used to test our various subsystems and is also intended to be used for demo purposes. One important thing that we were able to acquire from this assembly is that everything is a lot more rigid since it is metal and able to be mounted. And we were able to use calipers to measure various distances since the nature of this project is that there are a lot of dimensions that require very high precision for the loading system and the separating system and the launching system.
Okay, so here, I guess you guys want to start the video. Okay, so here's the prototype design of our separator system. As previously mentioned, it is made of an aluminum chassis kit that has a 3D printed cup holder attached, mounted onto it that holds the birdies. The cup has like an outlet that is wide enough to hold the birdies in place, but lets it go through most of the way. It also contains motors mounted onto the chassis that connect to the separators. our separators shown are pieces of rubber mounted onto the motors that would push and pull the birdie down out of the cup. And as you can see from the video, we are still figuring out the speed of the motors, but it gets the birdies out of the cup holder.
Okay, yeah. So obviously, one of the main issues is getting any birdie from the separator into the launching mechanism, which we'll go into in a short bit. For clarity, we're not showing the entire final design of the loader in the launching mechanism, just simply due to it's just kind of hard to see. But we started with kind of just like a little plate that would tilt and push it in. However, stability made us like, make it a little more robust. So we can see on the right here is the main two things here are the holder, which a servo connects to an arm, which will cock back to pick up any birdie that comes from the loading mechanism, the separating mechanism, and go into the launching mechanism. The way that this is carved out ensures that at any point that the loader goes through the wheels, it will not interact or then hit these wheels going at 10,000 RPM. The piece on the right is just a part of what we used in our, especially for a demo, it inserts rails into it to be able to guide the fall of the separator, because as you've seen in the previous couple of slides, the general trajectory of birdies is not always consistent without any form of passive mechanism. Moreover, to address concerns and the fact that in the future design, if we want this thing to tilt back and forth, the actual separator would not, in fact, tilt with it. We would want to make sure that the tube stays straight, generally keep it more finite. As such, one design requirement that could be expanded upon in the future, but for now, what we're doing is between each shot, the launcher will come back to its resting position. The birdie will load. It will then proceed to raise up to its ideal trajectory and then launch. That way we can ensure that, such a mechanism here is not, is receptive to, once we change angles, that you don't have to worry about will the birdie fall in the right place each time. So continuing on.
Continuing on to the launcher system, this is one of the first iterations that we had for launching the birdies. These ended up launching the birdie maybe 1 to 2 feet when we needed significantly more, about 15 feet. After this, we went and we did some more calculation and to realize in order to achieve the speed of a birdie once hit by a racket, which is anywhere between 200 to 300 miles an hour, with these size flywheels, we would need about, it was like 80,000 RPMs, something extremely high, extremely dangerous. So we went with bigger flywheels, still at a high RPM rate. I think we ended with around shooting for 8 to 10,000. And that high of RPMs did change up our flywheel design, as we will see in the next slide. Here is what we ended up instead with the flywheel design, starting with the image on the right. That is the enclosure holding the flywheels. You can see that the flywheels in there are a lot bigger and supported with 2 bearings on top and 2 bearings on the bottom per flywheel. This is to help any kind of wobble at that high of RPMs, just so the thing doesn't fly apart. And that enclosure is made out of aluminum in order to, in case there is some sort of failure and things go flying, there's a chance of it getting caught inside of that enclosure instead of getting launched out of the mechanism at dangerous speeds. On the bottom of that, you can see the shaft, and that ends up connecting to a motor to get our tilt in the up and down direction. If we look on the image on the left, that is the full assembly of our launching system for the final design. Our prototype does not utilize any kind of rotation up and down or side to side. This is just for our final design. Starting at the bottom, you have the motor that is connected to the rotary plate, and that is to allow for side to side rotation. The outer rim of that is mounted to that bottom plate, and that bottom plate is mounted to the chassis. And then the inner plate is what's connected to the motor, and that rotates. So the whole top half rotates side to side. And then on top of that top half, just the flywheels with the motors rotate up and down. This is how we achieved the 2 different degrees of freedom. Ideally in the future, kind of something we'd work towards is making this less bulky, minimizing it, condensing it, making it lighter, making it more product ready. But as kind of a, this is what we have for right now. Next slide. And so for the prototype, we go along the same lines where we have the enclosure with the 4 bearings and the spacers. Obviously, we don't really have the time or the funds to machine those enclosures out of metal. So we did 3D print them. These aren't necessarily safety enclosures, but instead to house the bearings. The wheel on the right is plastic with the plastic hub that we 3D printed while we're waiting for the actual wheels to come in, just for assembly and testing. What you see on the left is the enclosures ready to be mounted to the chassis, and with the actual flywheels from Andy Mark attached to them. This is still something that we are working on currently for the prototype, is assembling the flywheels to the enclosure. But that's something that we will have that done by Thursday or Friday of this week.
Yeah, and so this slide just shows the previous design iterations for the chassis. So the first 4 images on the left of the left side were the very first version, and they were meant to accommodate all of our subsystems. And at the time, a Raspberry Pi converter board, 2 motor controller boards, and Arduino Uno. So you can see that there are sort of corner holes on the chassis and on the plates that can slide in and out of the chassis. So it was made such that there's a top and bottom, and that they screw into each other, and that plates can be slid in and out to maximize the space that is contained within the chassis. And the top and bottom also have a semicircular cut because at the time we had sort of like a slot idea to move a rod that holds up the loading system and the flywheel motors. The chassis is also designed so it doesn't topple due to recoil or other internal or external forces. There are holes on the side for heat exchange purposes to prevent the electrical components and everything inside from overheating. The chassis was also parametrized with respect to the drivetrain model that existed at the time. We decided that this chassis wasn't fully functional or as functional as we wanted it to be. And so we moved on to another design iteration for the chassis, which is shown on the right.
So the chassis on the right, this was meant as a way for to test different variables for the prototype. So it was very, the chassis on the right is made without the drivetrain on the bottom, but out of wood and acrylic made from laser cutting, and housing the components in the housing, or the electronic components in the middle. And then all these, this was before we got the VEX hardware. So I tried to plan for moving variables of like where to place the tube or where to place the launcher. And so this iteration of the chassis was made to be built, and eventually it was built, but unfortunately it was very compliant. It would move a lot and rattle when ever we were testing our prototype, but it was good for giving us a measurement of where to place different things. And how we can improve the rigidness of the structure. Next slide.
Then for the chassis, the one on the left, that's the bottom of our chassis, which we made out of high density polyethylene. And so the bottom is what's housing the electronics and the battery. These will be mounted. We're not tapping screw holes into them because it's plastic, but instead fastening them down with self-tapping screws. And the motor mount attaches where the 4 screw holes are in the side of the chassis. This one on the right attaches to the top of that, and the separating and storage mechanism screws onto the top. Since we did get rid of the drivetrain at the moment for the final design, we attached it to a tripod. This tripod isn't one that we designed, but one that we found that's used for large camera equipment. So it can withstand the weight of our system, which at the moment is approximately 25 pounds. Next slide. Then for the, go ahead, Carlo.
Yeah, so this is as shown from the beginning. You have the VEX hardware machine as well as, yeah, so everything at the moment hasn't been mounted, but you know, at the time of this recording, we just recently got the wheels. So by the end of this week, hopefully we can have that mounted and axles can be cut and the motors can be attached to the top, as well as a loader system connected to this system. All in all, like we had a lot of iterations. The motors are actually not attached to this plate, but yeah, more will be soon, or more will be seen soon. Next slide.
And this is our final assembly CAD design. I think it'd be best if we just show it in SolidWorks. Okay, let's see. Okay, so this is the overall design. As I said, this is kind of the storage mechanism that's housed up here. And then if we remove this cover, you can see into the inside. There are still some slight changes that need to be made for the final design, but for at least for the mechanisms and mechanical side, it is just quite about done. There's some touch-ups to do with just user interfacing and aesthetics. But here, this is the bulk of the launching mechanism that we were talking about, with the 2 motors responsible for the 2 degrees of freedom. And then here in the back, we have what would be the battery enclosure. So the battery to go in here, and then the 2 PCB mounts. Kind of the things that we still need to do along here is adapt this to make the battery rechargeable, and a port for that, an on and off switch in the back here, and a way to sync a button to sync the robot to the user's phone in order to use the app that Annie will talk about later. And then also just wire harnessing mounts, just so we can demonstrate the layout of the wiring. But other than that, oh, and also the loading mechanism, which will attach here on the flywheel plate, one that's highlighted, because that will help bring the birdies down from the separator to the flywheel. Something that we noticed during testing time and time again is that the way that the birdie is fed into the flywheels makes a huge difference, and it is very finicky. That's why we decided to implement the loading mechanism so we have a consistent way and a reliable way of feeding the birdies time and time again to make the shots more reliable. That is about it for the final design.
Okay, so now I'll talk about the user interface. Okay, so just for a quick recap for the UI, we had this initial mockup and design on the left side and a static website on the right. Some features we have here are type of shot, birdie trajectory direction, time interval between shots, automated training, and calibration. And the plan was to have a single web page since we wanted to incorporate computer vision initially. So both the automated training button and the calibration button needed the use of computer vision, but since we decided that it was out of our scope, we decided not to include these features for our robot and do a total redesign of the UI. So since we decided not to include CV and we switched from the Raspberry Pi to using the ESP8266 microcontroller, we decided that we needed to first be able to display the UI differently by configuring the ESP8266 as an access point. So it becomes like a hotspot to allow other devices like smartphones or laptops to connect to it. So the screenshots here are just showing a successful connection to the network through mobile phone and laptop. So after establishing this connection, I then added our existing HTML and CSS code that I had for the previous UI to display the same functional web page designed previously. Okay, and then, so now all the user has to do to connect to our website is to connect to the Badminton Buddy network in your Wi-Fi settings, enter the password Team Erato, and then go to any web browser and type in this IP address. Okay, and so once we were able to configure the ESP8266 as an access point or hotspot, we worked on having the website read in user input and output it on a separate page when the submit button is pressed. So I also added calibration and debug pages for future use. And we also did a slight redesign of the UI by changing the color scheme and layout of the website. So here is the video. So yeah, we have the Birdie launcher. We have a new color scheme for the Birdie launcher, and I removed the automated training and the calibration buttons. So there's the debugging page. And yep, so as you can see, it displays the output given user input. Okay, and then, so finally, we completed a new website design for better user experience, making sure that the website adapts to the screen size, it's mobile friendly, and let's see. Okay, so here I'm just inspecting the web page to create another like tab of sorts. And then I'm just showing that if you change the screen size, the UI will adapt to it. So on your phone, it will be easier to read. Okay. And then here's what the Birdie launcher page looks like if you change the screen size. All right, and then we also made sure that we were able to get user input from the debug page and be able to control the servos and the motors given the user input. So here we have a video showing the debug page, and then you can't really see the motors turning. So here is the other video. So here you can see that the motors are turning after you put in the inputs into the debug page. Okay. And then finally, for our final version of the UI, we can generate these state diagrams. So we can either launch a Birdie as a user, so this way, or you can launch a Birdie as a developer, this path, or you can debug the launcher as a developer, so it'd be this path. Okay, and then now I will show the final UI. Yeah, so this is our final design. So if you're a user, you click on Get Started, you fill out the Birdie launcher form, you press Submit, and then it starts launching. It shows you the results right here. Okay, and then you can go back to the Birdie launcher and re-input values if necessary. If you want to go back to home, you can click on either Badminton Buddy or Home. And then the other path that I talked about was if you're a developer, so you would click on I'm a developer. And then here you can debug the 2 motors and the 3 servos. And then when you click on submit, this just shows that the user input was submitted. And that should be it.
Awesome. So obviously one thing to address then is that, from the beginning of the scope, we now want to see how it matches our final product. And some of the items determined to be in scope and not met that should be addressed was kind of from a general standpoint, the mechanical goal was out of reach from internal initial determination of the project. As we mentioned before, the chassis mobility was taken. A couple things that we, wanted to address, but then were unable to match would be the launcher angle mobility or having angle variation and differential testing for the shots themselves, thereby having a more robust system that can shoot when you're on the court. Just mechanical complications and overall inability to get into the testing phase early enough had to make us renege on that specific deliverable. And some methods of consistent separation, we have a lot of ideas that do work in theory. One thing then now to grow upon for the final product would be that consistent separation method over continuous time, multiple birdies. The last point is kind of, contingent on the launcher angle mobility, but yes, as such, we wouldn't be able to then test and guarantee the accuracy that was really important as an initial deliverable just due to the time frame and the revised goals of the final product. So on the next slide, however, this lets us then say, okay, so what are the future things we want to go into? First, Ethan, we're going to talk about the drivetrain.
Yeah, so one of the things that we weren't able to accomplish was the drivetrain, which we'd really like to implement in the future with more time. Since the main thing of our robot is not about the drivetrain, but is more about the launching and the separating and loading mechanism, we wouldn't necessarily design and build the drivetrain in-house, but instead find one that's compatible, maybe one that might need a little tweaking. Things that we looked at, for example, here we have the drivetrain of a t-shirt launcher, something that's relatively same size and same weight. Other things might be like a Roomba, those cleaning robots, a bulked up version of that kind of drivetrain, or other drivetrains of similar size that might easily be compatible to what we have.
And other things to mention really quickly is, again, we do really want to stress into the computer vision in the future. One of the big facets of our initial design and proposal was a proactive system that could then, make to a user, have a user come in, act, practice, learn how to play badminton, and as they get better, our robot would then be able to react and receive more accurately. Having this computer vision, having a more accurate system of player behavior would allow our overall product to just be that much better for the player. A couple other things, as mentioned previously, that as our first iteration of this final design does have a lot of issues with size and weight specifically. So working on making that a more compact cost efficient and just size efficient system is a major focus of our class. And reiterating the whole point is that our product as conceptually designed was an idea that in gyms would be a valuable tool to assist coaches in a way that allows training to be compounded and more organic and effective. So using those three points outlined, we do hope to one day, you know, if we had been given more time or had more like energy and resources to dedicate to this, we would have liked to, you know, really flesh out those three deliverables to make a really more accurate and useful badminton buddy. Thank you so much for watching our final design review. We appreciate it and have a great rest of your day.